Welcome to Sweet Spot Maths, the gold standard for A-level maths teaching. I'm David Forster. This lesson is on the modulus function. In recent years, the exam boards have come up with one or two quite tricky questions on the modulus function, where they say in their reports that hardly any candidates have scored decent marks. Therefore, for Sweet Spot Maths students, this is an ideal area to make sure you are on top of the material so you can gain the marks that the average candidate is just not getting. Just a reminder of the sweet spot maths method. We do maths in the sweet spot. In other words, we choose material which is fine-tuned so that you will achieve A star without wasting time. Secondly, we shift our perspective so we think like mathematicians, with the idea of completing even the hardest exam questions correctly and confidently. And thirdly, we focus on those exam secrets, the gaps, mistakes, and omissions of the ordinary candidate in order to gain a competitive advantage and get those last few marks and that A star grade. So let's dive straight into the modulus function. The definition of the modulus function is mod of x equals x for x being naught or positive, and minus x for x being less than 0, which gives rise to the characteristic V-shaped graph. The domain is the real numbers, and the range of the function is that y is 0 or greater. There is no inverse function, since the graph is not one-to-one. In other words, there are two x values giving rise to the same y value. The graph is continuous. It can be drawn without taking your pen off the paper, but the gradient is undefined at x equals naught. So, a few questions to warm up on this. First of all, we're given a function here, x squared take 3x take 10, a quadratic function, and I've drawn that in red on the axes below, the standard parabolic shape, cutting the x-axis at -2 and 5 and the y-axis at -10. Part A of the question says to sketch the graph of y equals the modulus of f of x. So what happens is those bits of the original graph that are above the x-axis stay where they are, but the part underneath the x-axis is reflected upwards in the x-axis to form this U-shaped graph with a maximum turning point in the middle. How many solutions are there of f of x modulus of equals 8? Drawing the line across at y equals 8, we see there are 4 solutions. The only thing we need to be sure of is that the turning point in the middle is going to be higher than 8. And given the intercept is at 10, it clearly will be. We don't need to know where the turning point is, just that it is greater than 8. Now, there are two shifts in perspective here where we can think like a mathematician. First of all, modulus questions are usually best tackled graphically and visually. We should visualize what's going on, not dive into heavy algebra without thinking about it first. And the second is, a question that asks how many solutions does not require us to find those solutions. So once again, work graphically as we did in this question. Exam secrets. For this question, examiners will expect obvious points to be marked. So here that would be the axis intercepts. And they will also expect the right general shape. What that means depends a little bit on the exact question, but here the general parabolic shape. So in the center, the U shape, the symmetry, and the maximum turning point. My next question here involves a cubic graph. In fact, it's the cubic graph that cuts the x-axis at 1, 2, and 3, which I've marked in red on the axes. The question is, part A, sketch the graph of y equals f of mod x. So this time it's not mod of fx, it's f of mod x. What happens in this case is when x is positive, that is to the right of the y-axis, the graph stays exactly as it was before. But to the left of the y-axis, it is a reflection, a mirror image of the graph on the right. So we get this graph with 6 intercepts in the x-axis and cutting the y-axis at a point at -6. So, thinking like a mathematician, y equals f of mod x will always be symmetric in the y-axis. Make sure you distinguish carefully from y equals mod of fx. And if you're not sure of the difference, go back to your textbook and do some basic questions to make sure you do know the difference between these two things. Part B of this question asks us to solve the inequality f of mod x is less than naught. So thinking graphically, we go back to our graph. There are 3 areas or regions of the graph where the graph is below the x-axis. They are between -3 and -2, between -1 and 1, and between 2 and 3. We need to be careful to write the answer correctly. In other words, to make sure we list these 3 areas separately, they are separate ranges, and not try in any way to combine them. To make sure we use strict inequality signs, we're not including the axis intercepts here, and make sure we use an or, not an and. X is in one of these regions, it's not in all 3 at the same time. And those are things examiners will be looking for when they mark this sort of question. My third question before we look at some exam questions will illustrate another common mistake. So part A, sketch the graph of y equals 2x plus mod x. We are mixing up here mod x and the raw x value. So what happens is, on the right-hand side, when x is positive, we get y is 2x plus x, which is 3x. So the characteristic graph y equals 3x to the right of the axis. But when x is negative, we get y equals 2x take x, which is x. So the characteristic shape of y equals x on the left-hand side. Part B of this question, how many solutions has 2x plus mod x equals 3? Drawing the line across graphically, when y equals 3, there is one solution only. It doesn't ask us where it is, but it is at x equals 1. Now, by jumping into heavy algebra, instead of thinking graphically, we can get a fake solution here and get the wrong answer, and I will show you how. Let's start with the equation 2x plus mod x equals 3 and take the 2x to the right-hand side. We now square both sides. It is true that mod of x squared equals x squared. So we rearrange to get a quadratic, which we solve and get 2 solutions. X is 1 or x is 3. There are not 2 solutions to this equation. There is only one solution. 3 is a fake. If you get to this position, if you now check your answers in the original equation, you will see that one of them is valid and the other is not. And if you do that in an exam and identify the valid solution, you will get the marks. The danger is that candidates will jump straight into using heavy algebra and write down both answers and finish, and will lose marks because the second solution is fake. Where has this second fake solution come from? It's actually the solution to the equation 2x take mod x equals 3. If you try and solve this, when you have minus mod x on the left-hand side and square, you get the same quadratic. So that quadratic gives you both the answer to the original equation and to this second one. One of the solutions we want, the other we don't. Now, some extra gold here. I've picked a question from, it's one of the Edexcel textbooks. It's one of the challenges. If you're a sweet spot math student, These are the sorts of questions you should be seeking out in your textbooks, the hard ones, the ones marked for the A-star candidates, the challengers. Those are the ones that will enable you to train in the sweet spot. So in this question, we're asked first to sketch on a single diagram the graphs of y equals a squared take x squared and y equals mod of x plus a. And we're told that a is a constant bigger than 1. So here we are. I've drawn the graph of y equals a squared take x squared. It cuts the x-axis at minus a and a, the y-axis at a squared, and has the characteristic parabolic shape. The graph of y equals mod of x plus a, where when x is 0, we get y equals a, and when y is 0, x is minus a, which is going to be the point of symmetry, the spike. Given that we know a is bigger than 1, a squared is bigger than a, which gives us the relative positions on the diagram. Part B of this challenge. Write down the coordinates of the points where the graph a squared take x squared cuts their coordinate axes. So it cuts the axes at minus a 0, a 0, and 0 a squared. My point here would be, if a question asks for coordinates, then you must write down both the x and the y coordinates, not just one of those. Examiners in general don't mind whether you use brackets or whether you write x is a, y is 0, but they do want both coordinates if that's what they ask for. Part C of the question. Given the two graphs intersect at x is 4, calculate the value of a. Now the two graphs meet in two places. On the left-hand side at minus a, that's clearly not 4. And on the right-hand side over here, that's going to be when x is 4. So we're on the right-hand side of the axis, we're in the first quadrant. So the equation we're solving is going to be x plus a, that's positive, equals a squared take x squared. Factorize the quadratic, it's a difference of two squares. And since a plus x cannot be 0 at our solution, we can cancel that factor to get a take x is 1. We're told that x is 4 at the solution, therefore a will be 5. Do make sure when you cancel any factor of an equation that factor can't be 0, and ideally say that, state it. Because if that could be 0, you're probably going to get an extra solution to the equation that you don't want to miss out on. Okay, on to an exam question. This was, I believe, from an Edexcel paper in 2020. So we are given here a sketch of a graph with equation y equals 2 mod x plus 4 take 5. And our first part is to find the coordinates of P. So P will be at the point when the modulus is 0. In other words, x is minus 4, and therefore y is 2 times 0 take 5, 4 minus 5. Once again, the question says coordinates. You need both of them, so we state both of them. Minus 4, minus 5. Part B. Solve the equation 3x plus 40 equals 2 mod x plus 4 take 5. So we're going to try and find when our original graph meets the line y equals 3x plus 40. That's going to be a straight line with gradient 3, so slightly steeper than our modulus graph, and the intercept is at 40, which is well off the top of our graph. Thinking visually and graphically, there is clearly going to be only one solution. It's going to be over on the left-hand side to the left of the vertex. So when we solve our equations, we are using the fact that mod of x plus 4 is going to be negative in that range. So we solve the equation 3x plus 40 equals 2 mod x plus 4 take 5, we can replace mod of x plus 4 by minus x plus 4 and solve, and x equals minus 10.6. Does my answer make sense? Yes, it does. That seems to be sensible from the diagram. Good practice is to check it works on your calculator. Now, if instead, or as well as, you had tried x is greater than minus 4, that is to the right of the vertex, you would have got a spurious fake answer. So if you dive straight into algebra without thinking graphically, you are liable to get two solutions, one of which is fake. Once again, if you get two solutions, check them in the original equation. You must identify the correct one if you want to get full marks in the exam. Part C. We are now told that line L has equation y equals ax, where a is a constant. So it's a straight line through the origin with a gradient ax, where a is variable. It's a parameter. The question is, find the range of possible values of a, writing your answer in set notation. So we think about this graphically. If a was 2, y equals ax would be parallel to this line and would not meet it. So a is not 2. If a was greater than 2, then definitely the line would meet the modulus graph once only over on the right-hand side. So a is greater than 2 is a possibility here. If a becomes less than 2, then initially the line will miss the vertex entirely. It will go below p and there'll be no solutions. But when a increases, or rather decreases, to a certain point, it will go straight through p. If a gets even more negative than that value, then it will cut in two places. So the thing to do is to identify what a value will make this line go straight through p. We know the coordinates of p are minus 4, minus 5, so we put that into the line y equals ax and rearrange, and that will give us a is 1.25. So when the gradient a is 1.25, there is 1 point of interception. That's fine. If a is less than 1.25, there are 2 points of interception. So our final answer is that a is such that a is larger than 2 or a is less than or equal to 1.25. Make sure you use a strict inequality here and a less than or equal to here, and an or, not an and. Now, this question, I've got the examiner's report on this question just to show you why this is such an important question for those of you who are learning the secrets in sweet spot maths. First of all, part A of the question was generally well answered, with most candidates being able to locate P correctly. A few candidates launched into heavy, lengthy algebra, in some cases resulting in values of x and y bearing no relation to the position of P. So the moral is, avoid launching into lengthy algebra, think visually, think graphically, and check your answers. Moving to part B, from this cohort of candidates, answers were very disappointing and displayed an over-reliance on algebra and poor understanding of modulus graphs. Very few candidates identified minus 10.6 as the solution. Most candidates wrote down a solution to 3x plus 40 equals 2x plus 4 take 5 as well, which would have scored 1 mark, a method mark, but not the final answer mark. If candidates just used the calculator to solve the equation, they would have got both marks. So perhaps not a bad strategy for weaker students. But a simple check on a calculator would have established there's only one answer to this question. So the moral is, again, check your answers, think graphically, think visually, and don't launch into heavy algebra until you know what you're going for. Part C. One of the most challenging parts of the paper, with hardly any candidates gaining all the marks. Candidates seemed unable to visualize the question and see directly that there would be an intersection if A was greater than 2, so they didn't get that mark. The method mark for considering P and attempting A as 5/4 was occasionally gained, though it often involved long-winded algebraic methods. So once again, think graphically, visualize, don't launch straight into heavy algebra. This sort of question, where you've got a line with a variable gradient or a variable intercept, is a very common type of sweet spot question. If you can do these questions, and in the second part of this lesson, I will show you another one of these, then you are getting yourself an advantage over candidates who don't know these techniques and don't think graphically. Now that is the end of the first part of this lesson. This is Sweet Spot Maths, the gold standard for A-level maths teaching. In the second part of this lesson, I will do another question like the last one with a variable gradient and a couple of other toughies from recent examination papers, just to make sure that no matter how many candidates don't get marks on these modulus questions, you do get those marks and do get the competitive advantage and the A star. If you want further information on Sweet Spot Maths for A-level, you can contact me on this email. Thank you for participating in the first part of this lesson on the modulus function.